Hello, welcome to this the 40th lecture in our physics of materials course. We have looked at a variety of different topics through this course, and so with this class we come to the conclusion of this course, and in this class we will spend a fair bit of time looking at one of the topics that I would like to discuss with you, which is the physics of nanoscale materials. So in this class we will look at several aspects associated with the physics of nanoscale materials and some of the reasons why this is of interest, and also get a feel for how what we have learnt it will in some way enable us to understand what this physics of nanoscale materials means, and perhaps how we can go ahead and appreciate the literature that is available in this area. So through this class we will do that, and then we will summarize this course and look at the various things that we have done through this course, right. So of course, as you know, these days there is a lot of emphasis on nanomaterials in general, the basic idea being that you can get a variety of properties in materials that we are already familiar with, but often when you take the same material and you keep reducing its particle size, then you eventually reach a stage where there is for most properties there is a dependence on particle size for the property, or at least several properties you will see a dependence on particle size of the property, and that may have a certain trend. But often it is seen that when you get down to the nanometer scale size scale, this trend can be either dramatically exaggerated or could even be dramatically different. Okay, so so you see some of these effects. Sometimes you see properties where actually there is no real great size dependence up to some point, and then after that point suddenly as you drop the size past some point there is a dramatic change in the property of the material. So what this is useful for is the general idea that you can now get the same material, essentially chemically the same material, giving you a variety of different properties, something that you can tune. You can say upfront that you would like a certain chemical composition but a certain particular value of a property, and then you can deliberately choose to prepare that combination, and within reason you should be able to do this depending on the general applicability of that composition or that system for the kind of property that you are trying to put it to use for. Okay, so this is the reason why there is so much of interest in nanomaterials, why there is so much of research in nanomaterials, and so much of funding in the area of nanomaterials. Okay, so this is what it is. We will look at these nanomaterials from the perspective of the kinds of properties that we have looked at, which is optical properties, electronic properties and such, and from that perspective what is it that is of interest to us. Okay. In this context, as I said, there is a sense of size scale. Okay, so so there is some particular size that you have to cross before this kind of change in property occurs as a result of the size scale. Now that size that we are talking of is not a fixed size. It is not that there is a universal size of 50 nanometers or 25 nanometers, that if you go below 25 nanometers everything will change. That is not how it is. For every property that you are looking at, there may be a particular size scale or even a range of sizes across which this property change might become more and more apparent. Okay, so that may be true for every that may vary for every different property that you are investigating. Not just that, even within a single property, even within a particular property that you have chosen, maybe a mechanical property, maybe a chemical property or an electronic property, even within that property, based on the material you are choosing, the size scale where the effects of the nano scale begin to show up may vary from material to material. Okay, so it may vary, the size scale that causes these changes to occur as a result of the being such a small sized particle, being a material made out of small sized particles, that may change depending on property, the size scale where that effect shows up, and also within the same property the size scale may vary from material to material based on the property that you are looking at. So this itself is an important concept that we should keep in mind. So there is no universal size scale at which everything happens, but we have to really look at the property and the composition and get a sense of what is that size scale which is now of interest, and when you get to that size scale you see properties of interest. So this is the important concept that you should look at. So it is important to keep in mind size scale. In other words, when is it that it is a nanomaterial of interest? You may have a nanomaterial, but it may still not be interesting because it may not be doing anything different from a bulk material. Okay. So, you have bulk material and a nanomaterial, and it is the size scale that gets you there, and exactly what that size scale is varies from material to material, varies from property to property. Okay. So, this is what we are looking at. Now, we will look at it from the context of what we have discussed in our course. So, in that relationship we will first start with something that we have that we are familiar with, and we will see what features of it start becoming of relevance from the perspective of nanomaterials. So, let us look here. We have drawn band diagrams before, and we will, for this purpose we will simply stick to a flat band diagram. So, we have some valence band, and then we have a conduction band. So, so far in our discussions we have really looked at how these bands come about, and sort of what are the what happens, I mean what is the phenomena related to this transfer of an electron from the valence band to the conduction band. So, we will assume it is a semiconducting material. Okay. So, so this band gap is less than 2 electron volts, we will say, and it is a semiconducting material, which means this valence band is full, the conduction band is empty. So, we have looked at direct band gap semiconductors, indirect band gap semiconductors. So, that talks about this process of the electron transfer from the valence band to the conduction band. What we will now discuss today is what happens after this transfer. Okay. So, we have talked about the transfer, the factors affecting the transfer, and what is the significance of it in terms of optical properties, how it tells you what is it in terms of what wavelengths will be absorbed, all those things we have discussed. But we will now see what happens after we do this transfer. So, what have we done after we have done this transfer? We now have an electron sitting here in the conduction band, and we have a hole sitting here in the valence band. Okay. So, there is an electron here. We have, when we do one transfer, we have electron in conduction band, and we have a hole in the valence band. Okay. So, this also we have we are quite familiar with, this happens. What is special about this situation? What is special about this situation is that we now have a pair of oppositely charged entities. You have an electron which is negatively charged, and you have a hole that is positively charged, and they are separated by some energy gap in the material, and location wise they are obviously not at the same location, otherwise they would just recombine. So, but anyway you have got this transfer in energy. Now, what happens is, because this is negatively charged and this is positively charged, there is a Coulombic attraction between the two of them. Okay. So, there is an Coulombic attraction between the two of them. So, therefore, they tend to actually maintain some connectivity with respect to each other. Okay. So, when you talk of a band, you normally talk of it as the once the electron has gone there, it is free to run across the extent of the material. So, and that is how you talk of conductivity and so on. What I am telling you is that in that process, every time you do this electron and hole entities, which we have sort of tended to talk of them as independent entities, what I am trying to point out is they tend to have some force of attraction between them because they are oppositely charged, and as a result there is an attempt on their part to sort of stay connected, to sort of maintain stay within certain distance of each other, and so when they move, they sort of move with keep maintaining this distance or staying within the limits of this distance. Okay. So, the force of attraction between them makes them more stable than a completely independent electron and a completely independent hole. Okay. So, and it is that and it is as a result of that they tend to stay connected and within a certain range of influence between each other. Okay. So, that is how it happens. This electron hole pair. Okay. So, the electron hole pair okay, is given a name, it is called an exciton. So if you read articles in physics, you read articles on in which are about the physics of materials, various articles you read, popular articles or even books, in books you will see this term exciton. It refers to this electron hole pair which forms whenever you have this electron getting transmitted through this which when it absorbs an energy and it goes up to the conduction band. Okay, so now we see some new thing that we have not really discussed. We see that this pair actually is sort of moving in tandem. It has some connection to each other, they have connections to each other, and so they have, so now you can sort of expect therefore that they may have certain properties associated with them, they may have certain limitations on what they can do, what they cannot do, and that may itself impact the properties of the materials that you see. So first thing we realize now is that it is a combination called an exciton. The other aspect of this which is of interest is the fact that what do we have here, we have one negatively charged species, an electron, so -1, and one positively charged species, +1. Okay. Where do we see a combination like this? Okay, so that is a question we should ask ourselves, where do we see a combination like this or rather where have we seen a combination like this which we are very familiar with? We have seen this in a hydrogen atom. Okay, in a hydrogen atom you have a nucleus which has a +1 charge and an electron around it which has a -1 charge. Okay, so in terms of charge and in terms of the number of entities involved, these two situations are exactly the same. The main difference of course is that in a hydrogen atom we are talking of a proton, we are talking of a proton and an electron combination. Here we are talking of a hole and an electron combination. So this is in that sense they are different, they are not the same, but there is certainly reason to see that there can be similarity between the two of them. Okay, there can be similarity, so it is sort of like a hydrogen like system that you are talking of here. Okay, and therefore in sort of the manner in which Bohr has treated the hydrogen atom, in the same context we can think of a sort of a characteristic distance that may exist between the electron and the hole, and this is therefore referred to as the exciton Bohr radius. Okay, so we have here so we now see that an entity called the exciton can show up, and it can have something called an exciton Bohr radius associated with it, which then represents the kind of distance that the electron hole pair can have between them while still maintaining this kind of a contact with each other or this connection with each other, so to speak. So this is the exciton Bohr radius, and as it turns out, unlike that for a hydrogen atom where you are talking of an atom is within an angstrom, this exciton Bohr radius can be of the order of nanometers. Okay, of several nanometers, it could be 3 nanometers, 10 nanometers and so on. So that is a large distance. A nanometer is 10 angstroms, so 10 nanometers is 100 angstroms, and so that means it is of the order of 50 atomic distances. Okay, so anywhere from 10 to 50 atomic distances is the kinds of values we are looking for in a Bohr radius. Okay, sorry, in an exciton Bohr radius. So it can be a relatively large number. It is not, in that sense you can see that it is not exactly equal to a hydrogen atom. Okay, so so this is an exciton Bohr radius. Fine, and what is and this is affected this exciton Bohr radius, as I mentioned, when you talk of materials, it really each material has its own properties. The phenomenon is the same. You are seeing this formation of an exciton is essentially the same regardless of what you are looking at, what semiconducting material you are looking at, but the actual radius is going to vary from material to material, simply because each material will have a different dielectric constant. Okay, so each material has its own dielectric constant. Now when the dielectric constant is different, it impacts the extent and manner in which the extent to which the electron hole pair are able to interact with each other or and therefore have an influence on each other. Okay, because they are oppositely charged, they would like to have they have a tendency to have an influence on each other, which is what causes this exciton. but what is the extent of this interaction and how far they can get away from each other and still maintain that interaction depends on the dielectric constant of the material. Okay. So therefore as a result you find that the phenomenon of an exciton will show up in the semiconducting materials, but the corresponding exciton Bohr radius can vary significantly from material to material. Okay. So this is one concept that we have. Now what happens, so when I said the size scale is important, we have to understand what is the size scale at which we start seeing these nanomaterial based effects occurring for that particular system. I said the size scale is impacted by the material we choose and also by the property that we choose. Okay. In our case, with respect to the band gap type of properties, the electronic properties, for many of the electronic properties, the size scale of interest is directly impacted by this exciton Bohr radius. Okay. So for a nanomaterial which is being used for electronic purposes, where you are reaching where you are trying to take advantage of some phenomenon that is occurring at the nanoscale and its impact on the material property, as long as you are talking of an electronic property, so to speak, electronic or optoelectronic property, the size scale of interest is not some arbitrary fixed nanometer, it is rather the specific exciton Bohr radius of that particular material. Given a material, given its dielectric constant and such, you can actually come up with an exciton Bohr radius. So once you know that exciton Bohr radius, whatever it is, like it may be 3 nanometers for some material, it may be 8 nanometers for some other material and so on. So we may have different values for the exciton Bohr radius, and based on the material you have chosen, this would then be the scale of interest, size scale of interest for you to start seeing nanoscale effects, and here for another material this would be the size scale of interest. So clearly there is a factor of 3 difference here. So when you make a sample out of this material, when you reach a certain size scale and you start seeing the effects of the nanoscale on the properties of the material, you will have to go to 1/3 the size before you start seeing the effects, the same sort of effects on this material. Okay. So it reiterates my comment in the beginning that both the property that you are choosing as well as the material you are choosing impact the size scale that you are looking at, which is where the effects of the nano material begin to take impact. Okay. So this is one issue, and incidentally what it means is now a nano material has to be made in these dimensions for those respective materials before you start seeing the impact. What is done in terms of nanomaterials for these size scales? From an electronic perspective, there are 3 terms that are often used. One is called a quantum well. Okay. In this, what is being done is these are all things that we will compare with a bulk material. Okay, a bulk material has a large crystal size and so on. Now you take a large bulk material and you start making it thinner and thinner till you finally get an extremely thin sample of that same material. So it is now a 2-dimensional material. Okay, what is a bulk material is a large 3-dimensional material from which you remove material till you get a 2-dimensional material. In principle, in fact, they do not normally do it that way, rather they grow it up that way. So you start with nothing and you grow atoms of whatever it is that you are growing till you get a very thin layer of whatever it is that you want. Okay, or you may even sandwich it between 2 different materials. So when you do that, you have what you have got is a material which has large dimensions in 2 dimensions, but it is very thin in 1 dimension. So you can have a very large piece of material, but it is very thin in 1 dimension, and so the 3rd dimension is extremely thin. And when we say extremely thin, this very thin is a very descriptive sense. This means you should get it to the around the exciton Bohr radius. Okay, so you have to get it get the value of this dimension to be very close to the length scale in that direction to be of the order of the exciton bore radius, then you start seeing the impact of that material. If it is much thicker than this, you will not, it will still look like a bulk material, you will not know the difference. You have to get it to the size scale before you start seeing that difference. So this is when you do it in when you do this only in one dimension, and you are actually, the electron is now actually free to move. In this case we are actually we discussed that we are now discussing about this excitons. In this case these excitons are sort of free to move in 2 dimensions, but in the 3rd dimension they have very limited mobility. Okay, so they when you talk of a quantum well, the exciton is now confined in one of the dimensions. So the exciton, this is with respect to the exciton that we are talking of. Okay, so with respect to the exciton which has also the same kind of size scale is now confined in one of those dimensions where you have made it extremely thin, and the other 2 dimensions it is free, it is relatively unconfined. Okay, so this is a quantum well. Then we have a quantum wire. Where you make an extremely thin wire of this material that you are interested in. So it is confined in 2 dimensions. And in 1 dimension it is free to go as far as it, I mean there is no confinement in that sense. And finally we have something that we call a quantum dot. Where essentially you are trying to make an extremely tiny particle of the material such that in all 3 dimensions it is confined to near about the exciton bore radius or even less. Okay, so in 3 dimensions, confined in all 3 dimensions. Okay, so on top we have the bulk material. From that we can convert to a material which is confined, so there is no confinement at all in all the 3 dimensions. You get a material which can be confined, where confinement of the exciton occurs only in 1 dimension, that is a quantum well, it is typically a very thin film of the material. You can confine it in 2 dimensions, that is a quantum wire, so that is actually a very thin wire, and then finally you can confine it in all 3 dimensions, in which case you are essentially having a tiny particle of the material, and that is called a quantum dot. There are of course lot of very interesting scientific challenges in doing this, because when you make such tiny particles they are usually very highly reactive, so they will not stay as tiny particles for too long. If you make such tiny particles they will simply react with each other and they will agglomerate. Okay, so when you make such tiny particles, one of the scientific challenges is to freeze them such that they do not get in touch with each other and grow. So normally, for example, what is done, one of the ways this is accomplished is to actually grow them inside a polymer matrix. Okay, so many of the polymers will typically have pores inside them which are in the nanoscale. So this would serve as a host matrix. So you take a host matrix consisting of this polymer. So you will have to analyze the polymer to understand what kind of porosity it has in it, or what kind of internal voids are present within it, and pick a host material which has voids in the size scale that you are interested in, which is the exciton bore radius of the particular material that you are planning to test. Then you grow this material inside this polymer. Okay, so and that can be done by various ways. You can actually make a salt solution of this material, get it to penetrate into the polymer, and then expose it to some gas so that it reacts and then forms the semiconducting material that you wish to have in that particular region. Okay, so therefore there are some interesting ways in which you can do this. So there is a lot of challenges here to get these materials made in the form that you wish to use. Okay, so that you wish to test it in. So in the process you can create all these things. You can create quantum wells, quantum wires, and quantum dots. In each of these things, in each of these cases, you are doing you are confining the exciton in some 1 dimension, either 1 dimension or 2 dimensions or in 3 dimensions. You are confining it. So what is the impact of confining an exciton? When you confine an exciton, within dimensions that is of the order of the exciton bore radius, then what happens is it impacts the band gap. okay. So it impacts the band gap displayed by the material, alright. So what you now have is a situation where the bulk material has a certain band gap, and by simply making it a nano material you can change the band gap, okay, because that changes the way in which the exciton is it is impacting the exciton combination, and as a result it is causing changes to the band gap, because the exciton has a certain interaction between the electron and the hole, and this is impacting it by making it in the same size scale, with the particle size being in the same size scale. So it impacts the band gap displayed by the material, and in general confinement increases the band gap. Okay, so it increases the band gap. Now this is of a lot of interest, because what this means is you can actually say for some particular purpose you wish to have semiconductors of different band gaps arranged next to each other, so that you can make specific semiconducting devices. Let us say that that's of interest. Often what happens is when you do this you can have with heat and so on, you can have some material diffusing into each other, and as a result over a period of time dissimilar material contact is usually a bad idea to have in most engineering senses, okay. So in many places in engineering we find that when we have dissimilar material contact there are a lot of problems associated with them in terms of sealing, in terms of any diffusion that might occur between them, any corrosion that might occur between as a result of that contact and so on. There are several problems associated with dissimilar material contact, right. But there are many places in the electronic devices field where you end up having to use a dissimilar material contact, because the band gaps that you are looking for and other such details may be different for different materials, and therefore you may need that combination to make it work, right. So now you have a situation where by doing this confinement for the same material you can change the band gap. What is more important is you can actually tune the band gap. Meaning if you do this carefully enough you can get a collection of particles of roughly the same size, all of which are different from all of which are near the exciton Bohr radius dimension, and since you get a collection of particles of essentially the same size, they will all have more or less the same band gap, but it will be different from the bulk band gap, okay. So you can have a set of particles which are now different from the bulk band gap, but they have a distinct band gap associated with them. So you can actually get a variety of band gaps with the exact same chemical composition, you can get a variety of different band gaps. So you now have the possibility where you can put together something where you have pieces of that component, each of which has a different band gap but has the same chemical composition. So you can now eliminate dissimilar material contact but still have the property variation that you desire, so that you can actually get the component to work the way you wish for it to work, okay. So confinement increases the band gap, and we by using this nanoscale all the impact of this nanoscale structure, you can actually tune the band gap and get materials with the band gap that you desire, and therefore you can use it with several advantages associated with the fact that the chemical composition is the same, okay. And so that is a big advantage. So for example, some of the materials that people work on are materials such as cadmium sulfide and lead sulfide, okay. So this has a band gap which is sort of in the somewhere in the visible region of the spectrum, and when you raise the band gap, of course it means that you can now it will now respond to the radiation of only higher wavelengths. So you can go from visible to UV, okay. So the same material you can get with a wide range of band gaps going from the visible spectrum to the ultraviolet spectrum. This is a material which actually has band gap more closer to the infrared region, infrared which is represented by IR, and with this material at the infrared region you can actually change its band gaps going all the way through visible to UV, okay. So you can change the band gaps in a dramatic way, and so the beauty of this is if you are looking for color of the material, when you are talking of materials which are actually going through this range of band gaps which go through the visible range, what it means is you can actually make a series of samples where all the samples have exactly the same composition, but they span the entire spectrum of colors that you are looking at. Okay, so you can sort of get paint of variety of different colors if you use this as your pigment, for example. I mean we do not want to use lead, but I am just giving you the as an example. You basically in terms of color you can get all the colors with the composition being exactly the same, and that is a very interesting and in a sense a very visible way in which you are seeing the quantum confinement effects on some of these materials. Okay. So, so therefore and that is just the that is something just for our visual perception. Of course in terms of actual usage you may find much more interesting band gaps and variations of those band gaps which you can cause by this quantum confinement effect on the based on the exciton Bohr radius of those radii of those materials. Okay. And therefore a lot of there is lot of technological interest in the nanoscale materials and what they represent in terms of the physics and in terms of what they can represent in terms of the devices that you can create using those nanoscale materials. Okay. So we have seen here that we understand now why is it that the nanoscale material has a certain property that we can manipulate, and that has got, as I said, with the fact that these excitons form and those excitons have some characteristic radii associated with them. In a sense they behave like hydrogen atoms, and then this is impacted by the material properties such as the dielectric constant, and then once you know this information for a particular system you can manipulate it. There are a lot of scientific and technical challenges in being able to do this manipulation. This is easy to say here to go from IR to UV, but to get any particular wavelength consistently is a challenge, but you can do it. People have done it and demonstrated it, and that is how these materials are used. So that is a brief overview of the physics of nanoscale materials from the within the purview of what we have discussed through this course. Of course there is a lot of as I mentioned, there is a lot of research into these kinds of materials, and there is a lot of literature available which looks at this in great detail. They look at cutoff wavelengths where something is absorbed and how that wavelength changes. There is a lot of studies on how these materials age with time and what are the factors that impact how stable those nanoparticles are and where you can use them. Even for solar cell applications you can perhaps find something which is a cheaper material but has the right kind of a band gap so that it absorbs most of the radiation that is falling on that material. Okay, because the solar energy has a spectrum associated with it. Only a certain fraction of it is the visible spectrum that we see. There is a lot of energy available in the spectrum which we do not directly see through our eyes. Okay, and therefore if you want to capture solar energy in its entirety and so that you can make use of solar power, you need materials which have the right kind of band gaps to absorb all of that energy and to do so very efficiently. Okay, so that you capture as much percentage of what is falling within that unit area. That would help you have smaller solar cells which are cheaper because it is of a material that you have chosen which is cheaper, but it is small because it is able to efficiently capture all the energy that is falling incident on it, and you are able to tap it. So a very so what we have just discussed is a very important input towards work that people carry out towards finding out alternate materials for collecting capturing solar energy and using it as an alternate source of power. Okay. So with this we will conclude our discussion on these its brief discussion on the physics of nanoscale materials. This is relatively an advanced topic because a lot of research is being done on this. It is still an ongoing research topic, and in that sense it is not in the same sense of a conventional undergraduate topic where the basic theory and understanding is very sound and everything is currently known. There is a lot of work going on in these areas. It's typically more of a postgraduate topic, so you may see postgraduate courses which dwell more onto these kinds of nanoscale materials and the physics of nanoscale materials. This gives you an overview of the major features associated with such types of topics and the discussions associated with them. Okay. So with this we will conclude this topic. What we will now do briefly is we will review what we have done through this course through a series of slides and conclude this course with a few specific comments related to where this course stands with respect to everything else that you are studying. Okay. So we will now look at a few slides. Okay, so as we come to the conclusion of this course, we will now briefly review what it is that we have done through this course more or less on a class by class basis, and that will give a very good feel for what it is that we have covered through this course and perhaps how it connects to anything else that you are presently learning. So we will do that, and that will give a summary of the course that we have and the material that we have looked at this point. So to begin with, we looked at we started off by looking at material science versus materials engineering, and in particular we looked at how we need what kind of approaches we would need to do to model materials, and also we considered the differences between theory versus experiment, in the sense that I particularly highlighted the fact that at the end of it all it is the experiment that is supreme, in the sense that if you are able to come up with a theory that cannot be proven by experimental in any sense with by experiment, or if there is strong experimental evidence that is contradicting your theory, then in principle the theory is not going to be accepted. So in that sense, in hierarchy, experiment is higher than theory. However, a theory may suggest that you have to try out new experiments, or perhaps have better control on how you run your experiment, so that possibility is always there. We then went and looked at properties of materials and some relationships between those properties to see what are the kinds of things that we should attempt to model, so that we can see if our models are actually correct, because like as I said, the model will be some kind of a theory which then has to match the experimental data given by those properties. Then we looked at the thermal expansion process, and in particular the E versus R curve, and we did this because in a single instance we could, in a single class we could actually see how we could build a model for a material from first principles and see an experimentally observed property which we can then and see how it matches that experimentally observed property. And so we spent we focused on this for an entire class. After that we got on to electronic properties, which required us to look at a lot of background material, but we started off by trying to understand why there is such a focus on electronic properties, and in particular if you are looking at conductivity, the fact that there is AC conductivity and there is DC conductivity, and what are the similarities between them, what are the differences between them, and under what conditions one of the property is one way of measuring it is more relevant than the other way of measuring it, and so on. So we did that in some detail. Then we moved on to the concept of a free electron gas, which we used for our initial theory of trying to understand conductivity. We looked at the rules that are used for this free electron theory for a metal and their implications. We also tried to reason whether or not it is reasonable to use the ideal gas laws to a solid. We looked at what are reasons why it may be acceptable, and also what are the reasons why it may be questionable to use such a approximation. In this context, since we were going to use specific relationships that are obtained in the ideal gas laws as part of our derivation of the free electron theory for the metallic systems, we actually went ahead and derived those particular relationships of the ideal gas theory, so that we could use them with confidence in our models for the electrons in the metals. The first model that we looked at in detail was the Drude model for electronic conductivity, and particularly how the Drude model was helping to explain electronic conductivity, what it gave as the trend for electronic conductivity, for the values for the electronic conductivity for various materials. That was the focus of our class here, and we compared what the model predicted with several experimental values, and we found that it actually did a very good job in explaining electronic conductivity. We then looked at the same Drude model, which is a free electron gas model, a classic free electron gas model, where the electrons are treated as classical particles and similar to an ideal gas set of atoms, and then we tried to see how good it was in trying to explain thermal conductivity, and again we looked at values from the literature to see if the thermal conductivity predicted by the Drude model was reasonable, and once again it turned out that those values were pretty good. So both of these were considered successes of the Drude model, and in particular the Weidemann-Franz law, which relates the electronic conductivity and the thermal conductivity, was very accurately quite accurately predicted by the Drude model, and so that was considered as a remarkable success for the Drude model. However, we also pointed out that the Drude model had some limitations in the sense that it was not able to explain everything that we saw in experiment. In particular, specific instances of the Hall effect were not clearly explained using the Drude model, and most importantly with respect to the prediction of the electronic contribution to specific heat, the Drude model overestimated this prediction in a very significant way. Okay, So in this context we try to explore the Drude model and aspects associated with it in greater detail, and we went ahead and did some calculations for the number of free electrons per unit volume, the specific heat at constant volume, electronic contribution to specific heat at constant volume, and related mean square velocity, drift velocity in silver, and we realized that at a fundamental level when we looked at these models we were using an energy distribution amongst the electrons as a very fundamental aspect of these models. So somewhere hidden in the model, even though we did not state it upfront, was the assumption that electrons were distributed across energy levels in a particular manner, and whatever we were predicting for the material was based on how this distribution existed, what was this distribution, and therefore how did the distribution change as a function of say temperature of the system. Okay, so this was something we identified as a very fundamental aspect of the model which was not immediately apparent when we did the model, and so we thought that we looked at the possibility that there may be errors related to this model which were the which were the source of the shortcomings of the Drude model. Okay, so this is something that we wanted to explore in greater detail. In this context we recognize that the systems that we were dealing with were actually electrons in a solid, which were a large number of particles, essentially 10 power 28 electrons per unit volume, and to deal with such a system we cannot just like that find out, even if you want to find out the mean square velocity, we cannot actually physically calculate the velocities of each of those particles and then find out the mean square velocity. So there has to be a different system to way of approaching such a large collection of particles, and that is the statistical idea of statistical mechanics. And in this context we discuss the central idea and central approach, central idea of the approach of statistical mechanics, and how it says that if you look at a large collection of particles, then the most probable distribution of those particles is then the equilibrium distribution of those particles. And so if you understand what is the most probable distribution of those particles, you get a good sense of what is the average property that the material is going to demonstrate as a result of assuming that that is the distribution of those particles. Having understood this idea of statistical mechanics, we went on to the and derived the Maxwell-Boltzmann statistics. Okay, the Maxwell-Boltzmann statistics applies to a series of a set of particles, a large collection of particles which are called classical particles, and so that is what this derivation was all about, and therefore this is exactly the statistical distribution that the Drude model assumes by saying that the electrons are behaving like atoms of an ideal gas, and therefore errors in say estimating the velocity or the energies of those electrons traces itself back to the fact that we have assumed that this is the distribution of energy of those electrons. Okay, so the distribution itself is the statistical distribution is correct, it is just that our assumption that it applies to electrons is not correct. Okay, so it is not that the math associated with the distribution is wrong, the math is fine, it is just that our assumption that this distribution applies to a collection of electrons is not correct. In this context we examined in detail what we mean by a classical particle and what are quantum particles. Classical particles particularly, I mean these are terms that we hear often, and therefore it was necessary to explore this in detail to understand exactly what is different between the two of them, so that we can incorporate those differences into the statistical the ideas of the statistics of those particles. Okay, so that is the reason why we looked at this in greater detail. And having understood that the particles that we are dealing with are not classical particles, electrons are not classical particles, they are quantum particles, we recognize that we have to now use approaches which are relevant to quantum mechanics to understand how the solid is going to behave. In this context we looked at the history of quantum mechanics, and particularly we did it because there is usually a lot of difficulty amongst a lot of people to understand quantum mechanics or to use it, and this is hardly surprising if you understand if you look at the history of quantum mechanics and the difficulty that the most spectacular scientists involved in this process had in also accepting quantum mechanics. People like Einstein lived their lifetime with a lot of doubt that quantum mechanics was correct. They actually he seriously doubted that it was right. He was of the firm opinion that there was a much more fundamental science that would sooner or later be discovered, which would not require the sort of what looked like arbitrary steps and arbitrary assumptions of the quantum mechanics. And so there is a lot of difficulty, inherent difficulty in quantum mechanics simply because of what it represents, simply because many of the things stated about quantum mechanics are not very intuitive for many of us. So that is why there is a lot of difficulty. and so at least we recognize that we need not be so surprised that we have such a difficulty in dealing with this subject. Then having looked at quantum mechanics, we looked at the assumptions of the Drude-Sommerfeld model, which is the model that takes the quantum mechanical behavior and imposes it on the on the original Drude model, and therefore tries to correct for some of the errors associated with the Drude model, and in particular it does so by changing the statistical distribution that is being assumed for the electrons. Whereas previously the Maxwell-Boltzmann distribution was being assumed for the electrons, the Drude-Sommerfeld model specifically introduced the Fermi-Dirac statistics and looked at how the Fermi-Dirac statistics can be imposed, the fact that this would be the more appropriate set of the statistical distribution to use for the collection of electrons that are there in a solid. In this context we derived the Fermi-Dirac statistics so that we get a good feel of what those how the statistical distribution is, how the fundamental nature of the particle impacts the manner in which we count the possibilities that can exist, and therefore how we incorporate the fact that it is a quantum mechanical particle rather than a classical particle into the statistical distribution. So that was the important reason why we looked at this statistical distribution, and we derived it in full detail so that we can take the result with confidence and understand what each of those terms means. Then we looked at the features of the Fermi-Dirac distribution function and its behavior with respect to energy and with respect to temperature. This is very important because the properties of the electrons in terms of the electronic contribution to specific heat, which was the big problem with the original Drude model, are all associated with these two aspects, the distribution of electrons across energy and how they behave with respect to temperature. Okay, so this is the very important aspect of that correction to the models, and so this is why we looked at it in detail here. So we compared then with our results up until that point with what had been obtained for the using the Maxwell-Boltzmann statistics, and in particular we looked at the specific heat issue and how the Maxwell-Boltzmann statistics or the Drude model dealt with the specific heat issue as opposed to how the Fermi-Dirac distribution and therefore the Drude-Sommerfeld model, which is an improved model, dealt with the same specific heat issue. In this context we then decided that even though we had understood now at least in a pictorial sense what was the difference between the Drude model and the Drude-Sommerfeld model and why the Drude-Sommerfeld model was better, why Fermi-Dirac statistics was doing a better job than the Maxwell-Boltzmann statistics, we decided we needed to have a better feel for what was going on in the material. So we needed more quantification of what was going on in the material. More specifically, as we discussed when we looked at the Fermi-Dirac statistics, the statistical distribution was giving us the probability of occupancy. It never told us how many electrons were occupying those states or how many electrons could even consider occupying those states. So it was necessary for us to understand how many states were available at each energy level, which required us to understand more about how those energies are quantized and how we can calculate those numbers. So in this context we built a realistic model to look at the potential in a solid and how to create a working approximation of the same. So we looked at how if you move an electron from infinity towards an ionic core, how the potential would change. If you had a series of ionic cores, what kind of potential atmosphere it would experience as it moved through the solid, and then we came up with an approximation for it so that we could do calculations with respect to it so that the potential wells looked a little bit more square. In this context we recognized what are free electrons, what are nearly free electrons, and what are bound electrons, and we differentiated these from a classical free electron gas. Having done that, we looked at the fact that electrons in a solid are confined, and we looked at the idea that when you do confinement you get quantization, and we explored this in great detail because this is a very central part of how the behavior of solids is seen and experienced when you look at it in this context. And then we looked at quantization using and the confinement and quantization using quantum mechanics and the Schrodinger wave equation, and therefore we were able to come up with an energy versus k relationship for free electrons, nearly free electrons, and for bound electrons. Okay, and we also found that that there was a spacing between allowed energy states for the nearly free electrons, and we compared it with the spacing between allowed energy states for bound electrons. We calculated density of states and derived the equation of density of allowed states as a function of energy and the density of occupied states versus energy, and this is what really enables us to understand to quantify the electronic contribution to specific heat. In this context we also looked at important concepts such as Fermi energy, Fermi surface and Fermi temperature, and we looked at their significance in terms of the properties of those materials. Then we looked at improvements over the Drude model, and as I said, now that we had all the tools in place, we were able to look at the electronic contribution to specific heat at constant volume as a calculated process comparing the Drude model with the Drude Sommerfeld model, and we identified the remaining limitations such as the anisotropy of the solid which had not yet been understood. We then looked at reciprocal space in considerable detail. We looked at its construction, we looked at how diffraction occurs in reciprocal space, what is the condition for diffraction, and what it represents, how it can be represented pictorially, and what it does in terms of how it relates to real space, in the sense that what happens to lattices which are simple cubic, FCC and BCC in real space, what happens to them when you look at them in reciprocal space, and in that sense we looked at the relationship between real space and reciprocal space. We defined what are Wigner site cells and what are Brillouin zones in 1 dimension and 2 dimensions, and we also defined what they are in 3 dimensions for FCC and BCC. And more importantly, we also looked at the diffraction condition, which we had independently looked at as a separate entity, but we now looked at it with its relevance with respect to the electron energy. In particular, we looked at the effect of Brillouin zones on wave vectors and the energy levels allowed, okay, and therefore how the energy gaps are likely to appear in the materials. In this context, we drew diagrams which we call the extended zone scheme, the periodic zone scheme and the reduced zone scheme, and we saw how the flat band diagrams, which is what the band theory is all about, how it compares with the E versus K diagrams, and how in this context of understanding that depending on the direction in the lattice the bands can appear at different locations in energy, we can understand the origin of anisotropy. The Fermi surface is the same, but where the Brillouin zone is different in different directions, and that is why we get anisotropy. We looked at a detailed calculation of how we can see based on our understanding of the material, and how by using the Schrodinger wave equation and solving for what the electron can do when the potential is 0 and the potential is V0, using that as a framework, how we can calculate what are the energy levels that are allowed and what are the energy levels that are forbidden. In this context, we looked at metal versus semiconductor versus insulator, and we compared the free electron approximation to the tight binding approximation. We built up this tight binding approximation and compared these two, free electron approximation and tight binding approximation. We also got a sense of how pressure might change band gaps by changing the interatomic spacing with respect to the tight binding approximation. Then we dealt in detail with semiconductors. We looked at the classification of intrinsic and extrinsic semiconductors, what happens to electrons and holes, what are electrons and holes, what happens to them in this context. We looked at Fermi energy for these semiconductors and how it changes from an intrinsic semiconductor to an extrinsic semiconductor, and we also looked at how the conductivity of semiconductors is impacted by whether or not it is intrinsic or extrinsic. In this context, we also looked at optical properties, and we looked at direct band gap and indirect band gap semiconductors, and they are used for optoelectronic materials. In the last few classes, we looked at magnetic properties in detail. We will try to understand what the properties are, what are the features of these magnetic properties, and also how the density of occupied states that we have understood through this course helps us understand magnetic properties. Then we went on to look at electron compounds, humero 3 phases, and again understand how our picture of the density of occupied states helps us understand why one phase is more stable than the other phase in relation to electron energies. And then we looked at phonons and what they are, what they represent, how they interact in the case of optoelectronic materials, and what phonon interaction does for indirect band gap semiconductors. We then went on to look at superconductivity in detail. We looked at the Meissner effect, we considered the BCS theory, discussed it, and we also looked at high temperature superconductors, and we noticed that in both in terms of the photons that we have discussed, the phonons that we have discussed, and the Cooper pairs that we have discussed in the BCS theory, that an integral part of all this was the fact that they were all bosons, and so in that context we looked at the Bose-Einstein statistics. And finally we finished off by looking at the physics of nanoscale materials, by trying to understand what is so special of the nanoscale that it impacts the physics of it, and how perhaps we could take advantage of it. Okay, so this is then the summary of the course. So we now come to the conclusion of our course. We have gone through all these topics, and we have also looked at a summary of it in the last few moments. So what we have actually done is, through this course, we started off this course at a stage where we basically said we have materials, we can measure their properties, and therefore we can use them. Okay, so this is the framework within which most of what is done in material science operates. What we have now done is we have tried to understand what is the source of, what is the science behind these properties. This is then the important contribution of this course. In this course we have looked in great detail at the science behind these properties, so that we now have a better sense of why is it that we are measuring the property, why is it that the value of the property is what it is when we measure it, okay. And by understanding this, we have a better capability of manipulating the materials to get the properties the way we desire them to be, and therefore this is a very important contribution to the general field of our ability to function effectively as material scientists, okay. So that is why that is the important contribution of this course. Of course no course is ever going to be entirely complete. So this is what we have discussed here will set the framework for you, the base for you to look at a lot of other courses, advanced courses in material science, in electronic materials, in devices and so on, where you can take all the basic concepts that we have learned here and understand the material that they are going to expose you to in those courses, and then and in the process help you become a more effective material scientist, okay. So with this we will conclude the course. I hope it has taken you from being able to merely use the materials to understanding how you can what is the science behind them, so that you can manipulate them and get them to serve your purpose even better, okay. Thank you.